accession and nuclear product and material science. Poster presentation number from 1 to 32. P001 to P032. After these previews, all of you are to move to the poster presentation hall, which is just behind us. And you may notice that so many presentations, therefore please excuse us to limit your message within 2 minutes. It's very hard. Okay? You may speak your name, of course. What problem you are addressing with the poster? Okay, maybe that's it. We kindly ask you cooperation to keep the time, and also for the other colleagues, for the other presenters, okay? And after preview, again, we'd like to kindly ask you to show up in front or nearby your posters. Maybe perhaps at least about 1 hour for the discussion with the other people. Okay, then let's start. And first of all, I'd like to Dr. Karabuto to show up on the top, because he does have 3 papers here. Therefore, I like Dr. Karabuto to speak his name and so forth within 5 minutes. Okay? 5 minutes.
Excuse me, my English is very bad. First report is named Access Kit Registration in high current density gold discharge, which various cathode materials. Hideo presented result of registration measurement, electric power and input and heat output for coordinate. Coordinate is device 2 quartz tube, cathode assembly and anode assembly. 3-channel cold water. Various material, palladium, deuterium-2, silver, deuterium-2, nickel, hydrogen, various materials, various gases. Current is 20 or 100 milliampere. Voltage is 300 or 800 volt. We restrict up to 20 watt excess heat by special cathode samples from Energy company. Maximum efficiency is about 200%. We have non-central result, but we have excess heat system silver on deuterium up to 10 watt. That's all. To report registration of high energy product in high current density gold discharge and possible. This is result measurement how high voltage pulses up to 10 or 20 kilovolt nanosecond during in gold discharge. X-ray or fast electron radiation up to 1 MeV energy. And the registration beta spectrum cathode samples after glow discharge. Spectrum up to 1 keV up to 1 MeV. We are illustrated beta spectrum for system palladium, deuterium, different materials, and palladium, argon. Result is following. It is possible to locate what type in nuclear reaction. First type, which formation radioactive nuclide, which are observed practically for unworking gases, including argon, and cathode samples from the majority of metal, which intensivity 10 power 2, 10 power 3, second power minus 1. A two-type reaction proceeding for some metal which hydrogen, deuterium by intensity 10 power 11, 10 power 12, second power minus 1, and forming stable nuclide which access heat without acceleration and radiation. Is that all?
Okay, Dr. Karam, thank you very much.
Report possible technological model initiating a nuclear reaction.
The next poster, mass flow calorimetric studies under non-steady state conditions by Crouchbaker, Makubri, and Tanzella will be introduced by Dr. Makubri.
Well, the problem that we're concerned with is the presence or not of excess heat during so-called Fleischmann-Pons boil-off conditions. Calorimetry is very difficult to perform under those conditions. We've performed several experiments observing the temperature rise as silicate materials deposit on cathodes, running the experiment into the boil-off or boiling condition in a closed calorimeter. What I have here is a result of one case where we observed with some confidence excess enthalpy. The black line is corrected, well, it's blue line really, is corrected for non-steady state effects. The green line is an uncorrected effect, but obviously the enthalpy goes from 0 up to something like 25 kilojoules in a relatively short time during the boiling of the calorimeter. The boiling period is from about here to here. Without the non-steady state correction, it's very difficult to get an idea of the temporal response of the excess heat. We make a non-steady state correction and we can fairly accurately characterize the enthalpy time profile. We performed this experiment several times with other palladium cathodes. We observed no departures from the calorimetric balance when the non-steady state correction is done in exactly the same way. We've calibrated this method of data analysis by using a platinum cathode in the same calorimeter in the same non-steady state corrections, and we observed an exact thermal balance. So we're quite confident that we are able, using our calorimeters, to observe thermal effects, excess heat effects during the boil-off condition, rather similar to those reported by Fleischmann and Pons in Nagoya. Thank you.
Thank you very much. Okay, next speaker is Mr. Dr. Dash. Dr. Dash, please.
studying electrolysis with sulfuric acid, heavy water electrolytes since 1989, since we seem to get reproducible results. And our results so far have been excess heat and unexpected elements which may have been the result of transmutation. The new things that we want to report here are one, we started to use mass spectrometry to analyze electrodes after electrolysis, and we think we have observed excess heat effect using platinum cathode. The mass spectrometer results starts at the surface and sputters away material, continually taking signal. What we find is on the surface, the natural abundances of palladium isotopes are inverted, but as more material is removed, it goes to the natural ratio. This happens in about 0.3 of a micron. With the palladium cathode, the heat effect is observed depending on the current density used, either very early or no later than about a day. With platinum, it takes a long incubation time, about 70 hours of electrolysis, and then we observed a similar heat effect, which we think is about 5 watts per gram.
Thank you. The next poster, from cold fusion to hydrex and Vujex states of hydrogen by Dufour, Fuss, and Mallove, will be given by Dr. Dufour. Are any of the authors in the audience?
If he shows up later, then we may let him speak. Okay, then poster number 007, excess heat experiment at 95 degrees C. Some values that I do believe they are here. Therefore, I move to the next poster 008. Improved open cell heat conduction isoparabolic calorimetry from Dr. Myers.
This calorimetry is an improvement over what we had been using, what we reported on this morning. Kendall Johnson was a postdoc. He was the one that did a lot of this designing. And the purpose was to measure more accurately excess heat effects in things such as deuterium absorption into the plate. And of course, I won't go over this, but this at the poster you can go over the things that we did to improve it. And we were able to get the noise level down measured within plus or minus 0.1%, where I've been measuring to plus or minus 1%, and plus or minus 0.2 milliwatts, where I've been measuring plus or minus 20 milliwatts. So basically factor 10 improved. And I particularly want to point this out. This shows when we turn the current on, this is the current here, this is excess power, we do see the heat of absorption of deuterium into the palladium. Somebody asked about this, whether we have any negative effect early on. You see this is zero power right here. Except for the absorption of deuterium into the palladium, we do not see any negative effect. It's very, very level, very, very close. Notice that this is 5 milliwatts right here. So we're measuring very accurately. We get about a 5 milliwatt effect during the absorption of deuterium into the palladium. And this corresponds to loading to about 0.6. This little peak right here. So this shows the accuracy we can get with this new calorimetry. Okay, thank you.
Thank you. The next poster slow nuclear excitation model by Kucherov to be given by Kucherov.
Okay, it's next to impossible to explain something in a couple of minutes, but anyway, here is my name, where I'm from. This is the basic approach. So if we have a heavy nucleus in a hydrogen or any other light lattice, we have a resonant quantum mode created by a quantum resonator. Then we have a chance to transfer energy at pretty high rates. And this is the picture of the nuclear quadrupole deformation induced by such a treatment. This way, we can get extremely high energy transfer to the nucleus itself. So here is, depending on the phonon frequency, the transfer can be about 10 to the 5 electron volts per second. All kinds of relaxation we can consider non-nuclear, nuclear, and pay attention. Probably this is where all the measured helium comes from. So this is an induced alpha decay of heavy elements rather than DD confusion. And this is the list of elements which can participate in this treatment. Now let me read the conclusion. The proposed model explains most of the existing experimental facts, actually all of them so far in fact. Any experiment which doesn't fit this model. Second, there is a time delay from 1 to 10 seconds depending on the phone, resonant phone mode, or starting from where you can see nuclear products. Helium flow observations are the result of alpha decay rather than DD cold fusion. Excess heat with light metal host lattice like nickel is the result of a heavy metal impurities.
Excuse me.
Okay.
You're almost running out of time.
Okay, I'm running out of time, but actually here are the predicted observables. And the last thing is that basically on the basis of this model engineering is pretty straightforward. Basically what we
Okay, thank you very much, Dr. Kucherov. Sorry about the short time. Next is Professor Lee Sin-tong. The title is Fine-Tuning Mechanism for Resonance Tunnel in DD Systems.
Of the light. In fact, I'm in charge of the 3 coasters. Okay. In fact, I'm in charge of 3 coasters. That's 10, 21, and 22nd. Last year, we proposed a formula for the resonance DD state. It has a long lifetime, about 3 hours. It can explain the excess heat without commensurate neutron, the center without lightning. And it explains the heat after death and the heat after life. It did introduce a question. For such a long lifetime, it's very narrow resonance. And its width is very narrow. How can such a narrow energy level in resonance with another very narrow energy level? So this year we proposed a fine-tuning mechanism. This fine-tuning mechanism will introduce a fine-tuning parameter. This is a critical number. The volume of the plating sample, the ratio to the heat transfer coefficient should be greater than this critical number. It can explain the experiment did by Mercury is positive, and the similar experiment in Australia is negative. And it explains why units of CIT report a positive result as pointed by Dr. Miles. It introduced another idea, the derivative of the density of the state of the neutron energy band should be negative. This is consistent with the neutron inelastic scattering data, and it is consistent with our excess heat in gas loading measurement. In fact, this will be the talk, my oral talk on the last day, the last talk. This talk will tell you the temperature difference between the twin system. One is deuterium, one is hydrogen. The temperature difference, the maximum value we measured is 8.5 centigrade. It's equivalent to about 3 watt excess heat in per cubic centimeter of palladium. Thank you.
Thank you. The next poster, cold fusion in electrophysical processes in ferroelectric deuterated crystals, influence of thermal neutron background level, pH substitution and crystal mass, will be introduced by Dr. Lipson.
As it was shown earlier by us on the transition through Curie point in DKDP crystals with the iteration degree 96 and 80%, the conditions of external thermal neutron background radiation, the excess emission of fast neutrons is observed. In common case, it may be amplification or attenuation of external thermal neutron flux passing through crystal in the vicinity of Curie point. As a result, emission of neutrons in these crystals can get positive or negative sign with subtraction of the ground wave. For high liberation degree, the sign of neutron emission is positive. For liberation degree 80%, the sign of emission in the high neutron background is California neutron cells is negative one. Simultaneously, in PKDP crystals, the suppression of spontaneous deformation defects and transformation are observed. In present work, we will demonstrate that the absolute value of neutron emission and its sign, positive or negative one, is dependent upon external thermal neutron flux, crystal mass, and its pH substitution degree. Thank you.
Just so you can't say we don't give people a second chance, I'll try it again. From cold fusion to Hydrex and Dutex states of hydrogen by Dufour, Fuchs, and Mallove will be introduced by Dr. Dufour.
You can use that microphone.
This one, okay. Yeah, I thought the preview was in front of the poster, so I have to move aside. But I will summarize very briefly the problem we addressed. We had experimental results showing reliable excess energy production, practically no nuclear products generated, except one on which we had some doubts, and probably some X-ray emission. So we tried to understand what could happen, and by using a simple quantum mechanics treatment, we have demonstrated the possibility of existence of a new combination between a proton and an electron, which is not a shrunken hydrogen atom, but which is actually the result of the equilibrium between the Coulomb electrostatic force and the weak electronuclear force. meaning that we have a small, very small combination of these two particles, something in the order of 5 femtometer, which is part of the time a virtual neutron and part of the time a proton surrounded by an electron layer of very small thickness. This is an hypothesis, but if you work out the consequences of this hypothesis, you can, I think, explain most of the observations made in the so-called cold fusion field, and we propose to call these species Hybrex and Dutex.
Thank you very much. Do we have Dr. Lu? Okay, then maybe later on. And then I may go to the B013 or 13. Reply to S.C. Jones and L.D. Hansen's concerning claims of Myers that involve plasma type photometric experiments to Myers again.
Some of you may recall Steve Jones wrote a very critical and harsh review of our work about a year ago last April. And we asked to publish a rebuttal back to back, but Steve Jones refused to allow us to do that. And we have now submitted a full-scale paper to the Journal of Physical Chemistry where this was published, but they've had it for 4 months and have not yet made a decision, so I don't know whether it will be published or not. So I'm giving in the poster section a condensed version of this. He criticized our calorimetry, and I'm not going to go over it right now, but our calorimetry is agrees very well with McCoubrey and Fleischman, Pons, other people in this area, and I think it's accurate. And we've had a person come in and evaluate it, and he agrees with our limits, plus or minus 20 milliwatts or plus or minus 1%. So I don't think that point that he made is valid on the question of our calorimetry. Another point is he makes it, in fact, he wrote 2 papers. One is on Faraday efficiency. And I think we look very carefully at Faraday efficiencies, like I mentioned this morning, by the volume of water displaced, the volume of detail required to make up what's electrolyzed, and the rate of gas development through the bubbler. So we're always looking at the Faraday efficiency. We know that it's 100%. It's not, excess heat is not due to recombination. He made another point about us changing our earlier detection limits. In our early results, we reported 10 to the 12. We later changed that. And we had to change it because when we did more accuracy for background, it was 10 to the 13. So it would not have made any sense not to change it. So our only sin, perhaps, was we were too conservative. We purposely were too conservative originally. We didn't want to claim more helium than was there, so we picked a more conservative limit. But using this background and subtracting it from our more recent results in metal flasks, we get the production rate is 10 to the 11th helium atoms per second per watt, which is about the correct magnitude. And in my opinion then, Jones and Hansen published a mixture of facts. Some are facts, but a lot of it is distortion and misunderstandings. And their look at recombination, they use current densities much too small, 1 to 2 milliamps per square centimeter. I don't know anybody that works down in that range. You need at least 100 milliamps per square centimeter. So their results do not apply to cold fusion studies. It's invalid, in other words. And I think our results provide compelling evidence that there is excess heat, and helium-4 is correlated with that excess heat. Thank you.
Thank you. The next poster, Field Screen Long-Range Nuclear Reactions by Horov, Miley, and Kelly, will be presented by Dr. Horov.
We are talking about how the neutrons or the protons can have conditions to initiate the reactions, DD, or reactions with palladium. Especially if it works with the surface or interfaces, where you have an electronic layer, and this causes a strong screening. I'm not talking what is the exciting result of George Meyer and others. That's the subsequent reaction that nickel excited causes in cobalt and alphas, and the cobalt makes them synthesize higher nuclei. I'm not talking about this. Now, first, let's remind us about the long range. The energy, the Coulomb energy repulsion is simply given from the elementary law. And it means, for instance, if a deuteron or a proton is moving with 1 MeV, it will reach then the 1.3 femtometers, the usual nuclear reactions. But if you have 10 keV energy, the distance is 143 femtometers, which means, for instance, the small deuterium is reacting with the hot fusion deuteron at 100 times the distance. This happens every day. Nobody wonders that over such a large distance the reaction happens. And the same is then if you plot then the reaction time for hot fusion, ionic fusion. There are measured values and the estimated calculated values from Rafalski and Hagelstein and so on. For the hydrogen molecule, you get a power plot. You do not get exponential law, because the gamma factor e to minus 100 would be 10 to minus 43. So we know from certain distances how reactions would work. And then we know the strong screening happens because every metal has electrons trying to leave the lattice, producing an electron layer. And from this you can get the double layer surface potential and the work function and surface tension straightforward.
Excuse me, you are running out of time.
Yeah, thank you. The conclusions. The semi-electron layer gives a reduction of the Coulomb repulsion. The quantum limit shows that only more than 2 eV protons or deuterons can react, and this means that no nuclear explosion is possible with our cold fusion. And the multi-layers can come up to kilowatts per cubic centimeter energy production.
Okay, thank you very much. Thank you very much. Okay, next, heat measurement during the electrolysis using modified palladium cathode by Professor Ota.
Thank you. As a poster, I'd like to show you our recent result of the heat measurement during the electrolysis using the modified palladium cathode. So these are the electrolysis conditions. Mainly, we're going to report on the palladium-containing balloon and also nickel-coated palladium. These are the electrolysis conditions, and the final results for balloon-containing palladium, we observed 6 times excess heat out of 16 experiments. Maximum excess heat we detected is 1.8 watt as an input power of 5 watt. For nickel-coated palladium, we observed very small excess 4 times out of 9 experiments. We also did some work on the so-called Patterson type cell using some special beads, but we don't see any excess at that time. Okay, this is a heat burst. We observed maximum heat burst is around 1.8 watt. And at the same time, we detected increase of the electrolyte temperature. please come over our seat and host the session. Please discuss with us. Thank you.
The next poster, triode cell experiments for controlled Fleischmann-Pons effect by Raglan. Is that in here? Okay, we'll hold that one. He's here. Okay. The next, P17, heat transported by buoyant force may augment solution convection in flow calorimetric systems by Schwartz. It is Mitch here. We're doing well.
Okay, then P0118 is anomalous increase in excess heat in the electrolysis of heavy water and light water for use of grilled cathode of charcoal. Dr. Takahashi, please.
I have been working using cathode this gas compound. Making a hole drilling only by electric drill in the surface of the cathode converges the current to the edge of the hole. And in the case of charcoal cathode, there is another effect of drill. It exposes the inside structure, that is, small, each vessels have very small micro holes inside the wall. So drilling can reveal the inside fine microstructure. Scanning electron microscopy showed the presence of the regular distributed micro holes in the vessels. By such function of these two by such function of these two effects, the current concentration and the exposing the micro holes, the excess heat of about 150% of excess heat was observed. And this method is very simple and very reliable method. So it was found. Thank you.
Thank you, Mr. Takahashi. The next poster in the list, 19, I don't think any of the authors are here, so we'll skip off that. The relationship of crystal structure transition of titanium cathode and excess heat on cold fusion by Zhang et al. And so, number 20, a high accuracy heat conduction calorimeter for measuring excess power in metal hydride and metal deuteride systems by Dominguez and Higgins will be given by Dr. Higgins.
If you don't mind, I'll do 3 posters at one time just to save some time. Posters 30, 31, and 20 are approximately, are somewhat of a summary of approximately 3 years of research at the Naval Research Laboratory on our examination of deuterized systems. Poster 30 describes our attempts to control the microstructure of the palladium, beginning with palladium sponge, high purity palladium sponge, and doing our own processing By arc processing, I mean arc melting, rolling into plates, and also swaging into rods. In addition, we also controlled the metallurgy by doing various temperature anneals, and then examined these effects by looking at the loading with a 4-point resistance measurement in an electrochemical cell. The long and short of all this was that we found that large grains appeared to load much easier and to much higher loadings than small grain material. But also there are some problems introducing, it doesn't address all the problems that you find by introducing various impurities into the palladium as you do this processing. And so there's some discussion actually in the next poster about impurities. In poster 31 describes X-ray photoelectron spectroscopy analyses of cathodes after prolonged electrolysis. We looked at both the NRL material, which I just described to you for poster 30, and also other heat-producing cathodes provided by other laboratories. Two of those laboratories, Mike McCoubry has kindly provided us a piece of his P15 cathode, which we looked at, and also Mel Miles has contributed several pieces of his cathode materials. And we've looked at all of these with the surface-sensitive X-ray photoelectron spectroscopy technique. In summary, I have found at least 20 different kinds of elements on the cathode. Whatever is in the electrochemical cell, it is safe to say, will land on the cathode. There is no question about it. But the question is, where are all the sources of these impurities come from? And on that poster, I try to give you an idea where we think some of them are coming from. Certainly we know the silicon comes from the cell, et cetera, et cetera. Platinum comes from the anode. Platinum could also come from the cathode if we consider any kind of diffusional possibilities. There are some other materials, other impurities that also could come from the cathode. By doing an impurity inventory using ICP analysis of the solution, also an inventory of the cathode materials and the anode materials using glow discharge mass spectroscopy, we have somewhat of an idea of where are all the impurities and where they're all coming from. And so there is some hints of that in the paper. The last one, a heat conduction calorimeter. Someone's name was left off of that. He's actually the most important person on that paper, and that's Roger Hart. He actually designed, it was left off of the program for some reason. He actually designed and built that calorimeter. That was one of the last things we did before our funding ran out, unfortunately, was to get this built and running. It's based on the temperature measurement is based on thermoelectric or CBEC devices built into aluminum blocks which confine our electrochemical cell. Our electrochemical cell is an open cell. Besides the normal input power wires, we also do our 4-point probe resistance measurements, and all those wires are all heat sunk to aluminum tubes, which are also heat sunk to the calorimeter. An important part of this calorimeter, too, is control of the bath temperature, which is done to about plus or minus 0.002 of a degree centigrade. The sensitivity of this calorimeter was 10 milliwatts or better, and the poster shows you some of those reference plots and so forth, and some of the determinations of the calibration constant. Unfortunately, we didn't get to use this calorimeter very much in what I would call prolonged, looking for excess heat type of measurements. Thank you.
Pat, the numbers in here are a little different than the ones that you measured out. I don't know if you've got the right ones, but anyway, they're down there at the end of the 30s.
Yeah, they're somewhere at the end of the 30s.
The next poster, number 22, a study of palladium metallurgical parameters aimed to achieving very high loading rates by Danilo, Barbera, and Violante, will be given by Dr. Violante.
So we studied the metallurgical parameters in order to reduce the effect due to the stress field which is produced when we load palladium with hydrogen or deuterium. On the basis of this concept, we performed some metallurgical treatment to materials in order to optimize the structure to have a preferential pathway which reduces the gradient concentration of deuterium inside the palladium. This is a simple cold work in palladium, and you can see a large concentration of defects. This one is material after cold water plus annealing at 800 centigrade for 4 hours. You can see these pathways for hydrogen diffusion in the bulk. And here we have the material after 5 hours at 1100 centigrades. You can see that the pathway disappears and the grain grows up again. And this is the behavior of such investigated materials. So you can see the loading ratio against the treatment. And we had a maximum above 0.95 at 900 centigrade annealing after cold water. Thank you.
Thank you very much. Next, 24 effect of cold work of palladium on electrolytic hydrogen absorption. Kamiya, Sakai, Watanabe, Yamazaki, Motohira, Okamori. Dr. Kamiya.
We have found that the cold bath of palladium gave much effort on electrolytic hydrogen absorption. This figure shows the relationship between HVAC and the extent of cold vacuum. These values represent the extent of cold vacuum. And the extent of cold vacuum increases, the HVAC decreases. On the contrary, this low value recovered to the high amount like this. This is the case of R90%. The HVAC increased under the high temperature annealing. We got to this large value, and this is almost the same as non-cold bath material. Thank you. Okay. Number 25, electrochemical loading of hydrogen, deuterium, palladium, and its alloys, Miles, Johnson, and Imam, given by Dr. Rose.
I should have probably done all three when I like Pat Higgins did. But anyway, this is a joint program, again, with Naval Research Laboratory. Dr. Imam made the materials. We studied loading by using the weighing method by how much gain in weight during the loading and how much is lost weight during the deloading. And this worked quite well. Actually, you would do measurements, take the liquid out of the solution, dry it, and then you'd wait over every minute for 10 minutes. Then you extrapolate back to 0 time and get the initial loading at the time you could get out of solution. These are the reactions, of course, as it loads. You get gain weight as deuterium goes into the palladium. I guess it didn't work, but and then as it deloads, you have the deuterium coming back out. So you could measure the loading by this method to the third decimal place. I'm surprised with that. You get quite an accurate value. And for the palladium boron alloys, of course, the smaller percent boron, you would get higher loading, as you see right here. But the main thing is the deloading. The deloading is very, very slow. I take out a solution over a 10-minute period, there'd be practically no weight gain. It would only change by 0.001 in a 10-minute period. But it shows that you can measure the loading very accurate. And as I mentioned this morning, the boron present deloading is very slow. It took almost 20 days to get back down to the original weight. Okay, thank you.
Thank you.
The next is poster number 26. In CT potential register metric measurement of qualified hydrogen absorption by vanadium electrode by electrochemical cathodic loading method by Dr. Mallove.
Our point is what happens inside vanadium, for example, mechanical properties during long-term electrolysis. To simulate this situation, we use the repeated adsorption and desorption cycle by electrical cathodizing and anodizing. And simultaneously, we measure the potential of electrode and also resistance and also dilation. And we evaluate, for example, mechanical properties by hysteresis of R over R0 versus hydrogen pressure diagram. I would like to show you one result. This shows the comparison of that diagram, resistance ratio versus hydrogen pressure diagram. The difference is this is a low-level loading ratio, less than 0.02, and this is high level. Hysteresis means this gap. Adsorption cycle, desorption cycle. This gap means hysteresis. This is small, and high level loading causes high level of mechanical stress or some default in the materials. Thank you.
Thank you very much.
Number 27, quantum mechanics approach for lattice ion trap, deuterons approaching mechanism in condensed matter by Violanti, DeMarco, and Hideo, given by Dr. Violanti.
The ion traps is a very well studied mechanism to produce interactions between ions on the basis of quadrupolar radio frequency confinement. We take advantages of a similarity between the palladium lattice structure and the above mentioned radio frequency traps. If we consider that the palladium atoms staying on the plane 101 and the palladium atoms staying on the plane 101 oversigned are in two planes that are orthogonal between, and the intersection of the planes contains the tetrahedral sides. We won't study what is the trajectory of a deuteron moving from an octahedral side towards the tetrahedral sides, taking into account that we have an oscillation of the electron flows around the palladium atoms. The oscillation of electrons produce an electric field, an oscillating electric fields, and then we can write the dynamic equation for these deuterons moving inside the trap. Here we have mainly the screened interaction potential, the trap force, and the effect of the shape of the potential around tetrahedral sides. And in the classical description, we obtain the trajectory of the deuterons moving towards the origin of the system in trap, where is located another deuteron. And we see that this mechanism can produce an approach which is below 0.1 angstrom. The quantum mechanical description is done by considering the quantum description of ions in Paul traps, like this one. And we can see that the probability to have a particle at a distance x from the central point of the track where the other deltas is located is a function of the function epsilon epsilon, which is the solution of the classical problem. So by introducing this expression for probability, we obtain a behavior like this, which is not in disagreement with the classical model. I have to remark that when the distance between deltas is below the screening length, Thomas Fermi screening length, the problem must be treated as a diffusion problem, because the quantum mechanical approach starts from the consideration that the particle moves like an harmonic oscillator having frequencies time dependent. When we are below this distance, the oscillator becomes anharmonic, and then we need to use the transition probability for diffusion problem. But the behavior is the red line I draw on the picture. Thank you.
Thank you very much, Dr. The question number 28.
Is Dr. Zhang in the audience ready to present either post number 19 or number 28? Okay. Then poster number 29, observations of strong resistivity reduction in a palladium thin long wire using ultra-high frequency pulsed electrolysis at D over PD greater than 1 by John Scaloni, Trivodi, DiGiaco, Dino, Marini, Di Stefano, and Mancini, given by...
Okay. Let me inquire the question. Who we are and what we are looking for and what we found. Okay, we are a study group of ISCMNS under supervisor of Celani, and we work with NATO and NHE and all in the Italian industry. What we are looking for? Okay, we are looking for overloading palladium wires, and I suppose most of you know this fluid resistivity of palladium under deuterium charging. And what's known is the loading up to 0.977 H over the PT ratio, and the resistivity normalized is 1.6. What did we found? Okay. After loading the wire and switch off the electrolysis, we observe a very low resistivity, around 0, and for a very long time, something like 1,000 seconds. And the transition to point the value of this curve. So it means I'm speaking about this kind of transition up to the number 2 is in a very short time, something like 1 minute, and this is the value of the resistance. Well, question? What other question we want to answer to the poster session? Thank you for your attention.
Okay, thank you very much. Okay, before getting into the post number 30, let me, oh yeah, okay, she's here, okay. Well, yeah. Okay, post number 30, in situ interferometric microscopy for palladium electrode surface and calorimetry during electrolysis of D2O solution containing sulfur. Oyama, Ozaki, Suzuki, Tsukiyama, Hatozaki, Imatsu. Okay, perhaps Dr. Ozaki, right? Hatozaki, sorry.
So we have been studying how substitution of electrode affect the production of excess heat. We carried out calorimetry in the presence of sulfur. Sulfur ion is expected to absorb on the electrode surface and improve the absorption of deuterium into palladium.
We observed a bath-like heat evolution during the electrolysis of D2O solution containing lithium sulfide, but not for a light water system so far. Also, we directly observed the surface topography change of the cathode by using a phase measurement interferometric microscopy. The palladium cathode surface became rough in the course of electrolysis due to hydrogen absorption, even at very low hydrogen content. But original surface is fully recovered by using this palladium as anode or just leave it in air for 24 hours to dissolve hydrogen from palladium. We also show some results obtained for palladium single crystals and palladium silver alloys. Thank you.
Okay, thank you very much. Let me try to find out some other authors. First of all, poster number 12, Dr. Lu. No? And then poster number 16, Dr. Lagran. Poster number 17, Dr. Schwartz. Okay, poster number 19, Dr. Zhang Ting Wu. Poster number 19, the relationship of crystal structure, transition of titanium cathode, and excess heat on pore fusion.
My work is about the relationship of crystal structure, transition of tight dot and X heat on cold fusion. We find no X heat, then no crystal transition. These two kind of experiments, they are the night water and heavy water through 24 days, no any extraordinary ascent of temperature. But the same spectrum shows there are deuterium and hydrogen in it. But the material still meant the titanium to jest hexagonal alpha titanium. But on the other hand, when we do 3 X heats, we find the titanium change the structure. This is the X-ray spectrum nice of tight dot before electrolysis. This is the X-ray spectral lines of tie rod are electrolysis with X-heat. So this spectrum is the crystal structure of TiD2. From this, we can say the tie atoms form a cube, a central cube. There are 8 deuterium atoms in it. So we can...
Yeah, excuse me, maybe you are running out of your time, but you can finish that.
Okay.
Okay, thank you very much. Continue the discussion. It's very interesting. And the next, perhaps we finally found Dr. Wu, correct? And this is the what's the number 12.
Good afternoon, ladies and gentlemen. My article's title is Election and Bounce Tape, and it's introducing of nuclear fusion and solar flare. In there, I want to discuss 2 questions. First, the generation mechanism, also called cold fusion, can be described by electron bound state and its introducing of nuclear fusion. Second, the solar flare, it is astronomy, and cold fusion are same physical process essentially. So I contributed maybe new concept and new research field. My point is give a strict description of quantum mechanism on electron and bounce state, 3 validation tests, and 2 approximate solutions are given, which is 1 corresponding to monoenergetic X-ray emission from PEP bounce state with EP about 12.5 kilo EV, and second, emission from D plus EP plus bound state with ED about 25 kilo EV, just double, and emission from D plus ED plus bound state with 25 kilo EV, which also introduced a little DD fusion to give out neutrons, protons, neutrons, helium-3, helium-4, and gamma. In this paper, some experiments such as nuclear hydrogen neutron gas glow discharge and are explained. The lineage about the excess heat is just a large quantity of X-rays released from 2 electron and bound states mentioned above, and only D plus ED plus bound state can introduce nuclear fusion. So, field analysis a large quantity of the measurements of solar flare nature spectrum and points out that the solar flare also contains the process of emitting many negative activity of about 12.5 kilometers EV and 25 kilo EV, and later introduced a little DD fusion. Thank you.
Okay, thank you very much.
We're going to go back to number 16, triode cell experiments for controlled Fleischmann-Pons effect by Dr. Rand.
I'm Ellen Ragland. I'm from Diamond Head, Mississippi, USA. I'm a retired electrical engineer. Like I'm sure many of you, I have been fascinated by the Fleischmann-Pons effect since the 23rd of March, 1989. I happen to look at the physics differently than other people. At Nagoya, 4 years ago, I presented a concept to explain the Fleischmann-Pons effect as I understood it. Since then, my interests have been to find a means for controlling the loading, the ignition, and the sustenance of the effect. About 18 months ago, the concept of a 3-electrode device was comprehensive enough to begin some experimental work. We have had very promising results from what we call the triode Fleischmann-Pons cell using D2O, solid palladium, and platinum anodes. I'm presenting the concept of the triode cell with a set of 12 posters. We have some 50 preprints in my paper. I would be delighted to spend whatever time you can grant me and invite you to come by my poster display. And I thank you for this opportunity to bring this to your attention. Thank you.
Thank you very much. And let me, do we have Dr. Zhang Kim Wu from, I think from Beijing, the Institute of Applied Physics and Mathematics. He should be here, in fact.
Our first session will be titled On-Call Fusion Activity in Russia, and the speaker will be Dr. Starr. The chairs will be Dr. Kim, Dr. Kozina, and Dr. Notoya. Dr. Kim, please.
Welcome to this evening session. Originally it was scheduled to be 1 hour for activity in Russia, but eventually there is a second speaker, Dr. Srinivasan, who will speak activity in India. So we will chair, 3 of us chair 1 speaker, 30 minutes. And Dr. or Professor Okamoto will chair next ceremony. Please, Dr. Sa.
Okay. Of course, I'm very sorry that I have only 30 minutes, and it means that I'll speak as much as our three beautiful chairmen will allow me, and then probably they will violently stop me. I'd like to say that due to some reasons, I didn't have a chance to attend last two Cold Fusion conferences. And now I'm very happy to be here. And I would like to say, go suritai arigato, go kyoriku arigato gozaimasu, sibaraku desu ne, hisasiburi desu ne. Okay. Anyway, roughly speaking, it means that I'm very happy to be here after a long break, and I appreciate very much our invitation to help to me and all Russian colleagues. Unfortunately, one of my colleagues, and he is a co-author of this report, Dr. Samsonenko, couldn't come due to problems with visa, so I'll present this talk. First of all, let me give you some personal estimate of general situation with science in Russia. 4 years ago at Nagoya conference, I described to you the process of decay, strong decay of USSR. And still now, the final state product of this decay are still in excited states. So there is no relaxation, and the economical situation is not stable. And as a result, nowadays, I believe our society doesn't want or is unable to support our science properly. Let me give you just some simple example. After presidential election, in many leading Russian institutes, our scientists didn't have their salary for a few months. And in cold fusion, the situation, of course, is aggravated due to rather negative attitude of the rest scientific community. Also, last year we lost one of our very well-known specialists in electrochemistry, academician Baraboshkin, who was a very strong supporter of cold fusion in our country, and we are very sorry about that, and we miss him very much. But despite of all these problems, we are still alive, and we are working, and of course we are asleep. For example, our activity can be shown in the following. During 4 last years, 4 national conferences of cold fusion were organized in our country. And here is some table of this conference. Unfortunately, the number of participants becomes less and less, and this is a result of the increasing of ratio between cost of this trip for this conference and the salary. The salary goes to 0, so the ratio goes to for example, tickets from Sochi to Moscow and back, and Sochi was one of the places the conference, is about 5 times larger than the average salary of scientific worker. But nevertheless, we are trying to do our best. We arrange conferences, and we try to invite our foreign colleagues. And here you can see a happy group of participants of one of our conferences. Now, about our pulp fusion. I'd like to start from the classical electrolysis, and I want to present a paper from Red Physical Institute group. This group measured particle emission from samples, sandwich samples, with this and this composition. These samples have been prepared in the Institute of Physical Chemistry and electrolytically loaded with deuterium and hydrogen. For measurement of products, three methods have been used: plastic scintillator detector, semiconductor detector, and CR39 plastic track detector. What's the observations? Proton and neutron emission during escaping of deuterium was observed, and the ratio of proton-like and neutron-like events was about 1. Also, some charged particles were observed during hydrogen escaping, and the authors believe that probably these are protons or alpha particles. Also, irradiation of the samples by low intensity flux of thermal neutrons was done, and it was observed that in this case the intensity of fast neutrons increased about 300 times in comparison with the same flux from unexposed sample. And here is some picture of detector for neutrons and some results. I don't really have time to some spectra received with semiconductor detector, and this is results from plastic track detector. And this is a picture of plastic track with some spots due to penetration of charged particles. Okay. Now, I already mentioned the group from the Institute of Physical Chemistry, and they also studied these samples, this type of samples, and they observed after loading of these samples and drying it, they observed 3 effects. First, some large heat excess heat bursts. Large means that from 2 to 5 times larger than input energy. Then they observed neutrons in the case of deuterium samples, and they also observed gammas, both in the case of deuteron and hydrogen, and also they observed some dependence of the effect of the flux of thermal neutrons, the ground flux. And here are the results with gamma emission, and they observed 3 peaks, and 1 peak corresponds to well-known peak 2.2 MeV energy, and 2 other peaks at larger energy. Probably they correspond to other possible reactions. Now, another approach, gas discharge experiment. Still 2 groups from which association in Podolsk are working in this field. The first group, led by Ramadanov, presented 3 results to this conference. First is related to tritium production with metallic cathodes. The main results of this study is about 4 or 5 years study, are the following. First, they observed that the rate of tritium production in condensed metal is about at voltage about 10 to the 4 electron volt of the deuterium ions exceed the calculated rate for thermonuclear reactions by several orders of magnitude. Second, the neutron to tritium ratio is very small, typically it's 10 to the minus 9. The rate of tritium production increased with increasing of atomic number of the target and with the concentration of admixture of hydrogen. They also observed that there is some sort of threshold effect, and this threshold is about 100 electron volt. The next point is that the ratio of tritium production is more or less linear function of current density. And the last point is that the nuclear interaction efficiency, or coefficient, which is a ratio of tritium per one interaction, is maximum at about pressure 10 to the 4, 10 to the 5 pascals. And here some picture which illustrate this result. So this is that coefficient of nuclear interaction in atom per interaction as a function of density, current density. You can see more or less linear dependence. And here I have also some picture of history of one of the sample. It's produced some increase and quite easily visible about the average background. This group also presented results received with ceramics. They used this kind of ceramics and they tried to measure tritium and gammas. For tritium, they observed for this type of ceramics is rather high signal of tritium production. However, they practically didn't observe any gamma radiation, and their limit, the gamma to tritium ratio is about 10 to the minus 3 or less. The last paper presented to this conference, submitted, is tritium generation and transfusion of hydrogen isotopes through the targeting plasma of low discharge. So, in addition to their usual experimental procedure, they use the transfusion of gas. And gas can be deuterium or hydrogen. And for some of the materials, cathode materials with deuterium, they didn't observe any effect. For molybdenum, they observed not very high, but about 2 times larger effect in this case. And for molybdenum with hydrogen transfusion, they observed rather visible decrease of the effect. And I'll show you this result. Here is the nuclear interaction coefficient and time of this process. And also, I know that Dr. Magana brought some new results, and he considered this result as very interesting, extraordinary interesting. But he asked me to don't speak here because he would like to keep you in some excitation, and he hoped that he will have a chance to present it himself. I'm sorry. It's just my commercial advertisement. The other group from the same institute, Karabut, Savatimova, and Tada, continued to study transmutation phenomena in palladium cathode after irradiation by ions in low discharge. For cathode, they used various materials, And for gas, they also use deuterium, hydrogen, argon, and xenon. And they observed both impurities and isotopic shift in their samples. Here you can see some parameters of their work, and they observed a lot of various new elements. And here you can see the results. So this is a nucleic content in palladium after neutron glow discharge. And here is atomic number and content. You can see many elements. So this is palladium with deuterium. This is palladium with hydrogen. Also, there are some new elements. And here is palladium with argon. And in this picture, you can see the isotope shift in palladium after the deuterium glow discharge. So you can see the increase of some isotopes and decrease of some the palladium. And the other paper presented by this group is related to colorimetric measurement. So they try to observe heat in glow discharges and excessive heat, and see is there any correlation of the heat with impurities. And they really observed such correlations. And this is illustrated in this figure. So this is their setup. I'm sorry. This is another setup with the constant flow colorimeter. And here's some results. So a lot, again, you can see a lot of impurities, signals from impurities. This is excessive heat. This below red line, it's electrical power input, and above is excessive heat. So you can see that there is a sizable effect. And they observed that there is a real correlation between if there are more impurities, more heat. The other problem, nuclear phenomena and data-rated ferroelectrics. Two experimental groups now are working in this field. First is People's Friendship University group, and they studied various kinds of ferroelectrics, data-rated ferroelectrics, and they used the alternative current field applied to these ferroelectrics, and their results are the following. They observed the neutron emission during this process of inverse polarization, or reverse polarization. It's not very high. It's about 1.5 or 2 times the background. The absolute value are shown here. And they observed that for thin dielectric plate, the effect is larger. Probably it's related to higher electric field in this case. So here the schematic view of the setup and results. You can see here for thick and thin sample. Red is average background, and there's some excess of neutrons over background. The other work done with ferroelectrics is the experiment at Institute of Physical Chemistry. They measured neutron emission with deuterium data-rated ferroelectrics during phase transition near Curie point. And they also studied the role of thermal neutron background. What they found? They found that there is a neutron emission, and the sign of this emission or effect, I'll explain it later, strongly correlates with the 3 points. First, with thermal neutron background level, with the deuterium to hydrogen substitution ratio or saturation ratio and with the mass of crystal. They observed, for example, that when X is close to 1, then there is positive neutron emission. What does it mean? It means that if they irradiate their sample during phase transition with very low intensity neutron, thermal neutron background, which maybe it's not too low, but it's about 100 times larger than the natural cosmic ray background. They observed that in this case the emission of fast neutrons also increased about 20 times. At smaller x equal 0.8, and at cosmic ray background, they observed very small, practically negligible effect. And at the background, which is about 100 times larger than cosmic ray background, they observed strong negative effect. It means that there is no excess of the neutrons in comparison with not irradiated sample, but quite opposite. There is a lack of fast neutrons. And they also observed very interesting features, just rather amazing. They observed that there is a shift in the value of Curie temperature, lowered about 4 degrees, when they use weak irradiation of their sample. So here you can see the results. This is a transition of Curie point, and there is some neutron excess. And here you can see positive and negative effect, which I already mentioned. The other subject is cold fusion in tungsten bronze structure and proton conductors. First of all, I would like to remind you that at Nagoya conference there was a high interest in this type of materials. And I know that Khalif now is working at Dubna. However, my attempt to find him, especially in Dubna, was unsuccessful, so I know only some details. So he is continuing his work, and he claimed that there are some positive results, but I don't know any published results. The work with the same material is also going in the Institute of High Temperature Electrolysis at so they try to understand, is there any difference in the structure of these crystals in the case when they produce neutrons and in the case they don't. And they really observe that there is correlation. And their statement is the following. There are some changes in structure layer perfection correlated with neutron activity. Neutrons are produced in those samples which had some transition from perfect near surface layer to mosaic crystalline structure. In the same institute, there is another work was presented from the same institute, this time with molten salt electrolysis with lithium tetride. So it's very close to the ideas of Leon's ideas. However, they use a little bit, maybe more interesting procedure. They use in parallel two cells, one with data materials and another with hydronide materials, and they can measure that directly the difference between these two cases. And their result, if they use the direct current for electrolysis, and the current density was about 4 milliampere, And after 24 hours, there was no any difference between these two cells. However, if they used variables, current, I'll show you the picture, variation from 4 to 290, from 4 to 420 milliamps. Then they observed really sizable increase of temperature, heat effect. So pictures. This is their two cells with the laterite and hydronite materials, hydrogenite. And this is the result of the calorimetry. You can see some increase of temperature. The same group presented some interesting result on with ceramics. And I will not describe their procedure. Let me just show their results. They observed that there is excess heat which varies in different situations from 10% to about 1000%, 10 for direct current, and much larger for reverse current, and sometimes they also use thermocycling. And they observed, they believe that they observed phase transition in this material first time in observation, and they believe that this effect is related somehow to the phase transition. Now, when they used instead of deuterium hydrogen, the effect was rather low, only a few percent. The typical value of increase of power was about 2 by 10 to the minus 3 watt, so it's very low level. And they also observed a neutron boost. However, it was not correlated with excessive heat. Now, it's wonderful. Maybe first time I have time for the theory. Usually I don't have. So let me say a few words about theory. So no money, but there are some ideas. First of all, I'd like to present you a paper on unitary quantum theory approach for cold fusion. This approach is developed by Professor Sapogin quite a long time. And in this case, in contrast with the standard theory, particles considered as not, or described as not point-like object, but as a wave packet. And the formalism can be reduced to well-known results in some special cases. So in this case, particle is a periodically emerging and disappearing charge, wave packet with oscillating charge. And in this case, Professor Sapogin can explain practically all phenomena which are observed in cold fusion experiment. So he can explain tunnel effect, p-channel suppression, excess energy, nuclear transmutation. Maybe you would like to ask him more. Please, he is here and he will present his results. Now, let me mention also 3 papers very briefly from Leibniz Physical Institute. First, in first paper, we are discussing instability or current instability effect in experiments with very highly loaded hydrides. The aim to call your attention to some physical phenomena related to non-linear influence of electric field or currents, current carrier mobility, which could manifest themselves in cold fusion experiments. In fact, such phenomena very well known in semiconductor plasma physics. And our idea, first of all, is that, from our point of view, there is a similarity between hydrides, especially when they are overloaded, and semiconductors. In one case, we have electron plus holes, in other electrons plus protons. And the key assumption of the paper is that at very high X, there is a transition to non-metallic state. Maybe it's semiconductor or something, non-metallic state. We cannot prove it rigorously, but we have some semi-quantitative estimate, and I don't have time to discuss it. I just show you. This is a result from San and Thomas paper, and they calculate the density of states for deuterium, deuterium hydride, and deuterium H2, and they really observed what we are predicting. They observed a gap, and Fermi energy is just inside a gap, and it is known that this is a situation of transition to non-metallic state. And this is shown in this picture also. If so, then we are able to show that in this case, we can calculate using this result the resistivity or resistivity. We can show that when you change X from 1 to 2, the resistivity can increase 3 or 4 orders of magnitude. And in this case, we analyze the situation, and we were able to show that in this case, the negative differential conductivity can be realized, just as in the case of semiconductors. And well-known situation can be realized with S-type or N-type instability. And this, I'll show you what will be the result of confusion experiment. So with some sort of instability, the sample is divided in several layers with different value of electric field, or current can be divided in different streams. And the other possibility is to have pinch effect. Now, what is the manifestation in cold fusion experiment? There are different possibilities. First, nuclear effect due to current compression. This is maybe most interesting. Due to pinch effect, you can produce current pinch and squeeze neutrons. The other possibility is the acceleration of neutrons in high fields. And the third possibility, the heat also can be produced in some very non-trivial way. But anyway, I'd like to finish this paper. We would like to call experimentalists to verify this effect. It may be interesting not only to cold fusion, but also to metal science and electrochemistry and some other. Now, I don't have time just to say. The other paper is about possibility to increase efficiency of initiation of nuclear reactions in ferroelectrics. In fact, some years ago we initiated this activity. However, all experiments which have been done after that were done with far from optimal conditions. So we are discussing how to make this condition more favorable. And the main idea is that the main problem is tunnel breakdown. How to avoid this effect? It is possible if you create some instability. And for that, you need special shape of pulse, a very large, very steep frog. Last paper. The last paper is, in some sense, related to the previous. We can see the type of this paper. Is it possible to produce hot fusion in cold matter? And the answer is yes, probably, maybe. Yeah. So, using selective heating with laser, we hope to produce. I don't have time. Maybe I'll have a chance to present it at poster session. Thank you very much.
Thank you very much presenting 1 hour talk into 35 minutes talk. Presumably you are leaving us in excited state by doing that. Is there any questions or comments? Yes, please.
One question about the
microphone.
One question about the quality of surface and neutron production. You said that very good surface, you have neutron production. When the surface was not so good, you have no neutron production. I don't know whether you can all these topics remember what you were saying. My question is, to what degree could one distinguish between a good surface and not a good surface?
What experiment is
It was an experiment.
experiment?
An experiment, let's say you said 10 minutes after you began, about neutron generation in cases you had very good surfaces, and when the surface was not good, then you have no neutron production. I forgot who were the authors.
Neutron result which depend on surface.
In ferroelectric.
No. It was in palladium.
In tungsten bronze?
Yeah, no, before bronze.
In palladium.
Was palladium.
What experiment? I don't understand what experiment you're asking about.
I discussed
Surface. Yeah. Heat.
So how to explain potential surface?
Potential of surface.
Are you talking about one of the geographic shown? Well, maybe you can discuss.
I really let's
discuss.
But we
Any
need
other comments? Okay, let me ask one more question, which is, how many of those experiments you reported?
It's about 30. No, for experiment about 25.
25. Out of 25, how many of those are repeatable?
Only in one paper there is a claim that they have practically complete repeatable results. And incidentally, I didn't show it. I didn't have time. Yeah. But general situation is more or less the same for the whole this type of experiment.
Okay, thank you very much for your presentation. Next speaker will be introduced by Professor Kojima.
Next speaker will be Dr. Srinivasan from India on the code creating activities in India. Please.
Thank you very much, Mr. Chairman. Let me assure the audience at this late hour in the day, I will not be presenting any detailed paper. I was requested to give just a very brief overview of the activities in India. From my point of view, just to give the impression, work is going on, we haven't wound up. We are facing the same kind of problems that many other groups in the world. Problems of non-acceptance of the subject on the one hand, and problems of non-reproducibility of the experiment. So with this background, I'll just very briefly go through some of them. In some cases, I'll try to give qualitatively some results. I think I have to stay here. Firstly, all the work, when I say India, it should be restricted to the Baba Atomic Research Center, because essentially all the cold fusion research is going on only in our center. There used to be some work at the so-called Indira Gandhi Center for Atomic Research in Kalpakkam, but those groups are more or less wound up. And recently, we were able to start some work at the Indian Institute of Technology in Kanpur. A very young and very enthusiastic scientist started his, but so far no results. And I have during the last year visited almost all the IITs in India, giving lectures, trying to convince the mostly the professors, immediately it turns out the young people are much more open-minded. They are able to accept and receive ideas. It is the older professors who find it very difficult to give their blessings. But there have been some cases that people are willing to try. Mostly the problem is that people do not want to assign cold fusion as a doctoral thesis topic for the simple reason there is no guarantee that the student will finish it in 3 years or 4 years. And that's why they don't want to. University are finding it very difficult to start work in the area. Now, the work at VAC, I'm dividing into 3 categories. The work done in the division to which I belong, the so-called neutron physics division, where we have been looking for neutrons. We reported last year the production of neutrons from a Milton-Roy electrolytic cell. And at that time, we said there was an increase of about 9% in the average count rate over a 1-month period. But one little point we missed there was we did not take counts with the cell switched off. So many people even at the ICCF-6 asked me the question, how do you know that the increase in count rate is not simply because you are introducing a cell containing heavy water and palladium into the... So that was the point which we had missed, although we ran the cell with light water, which we reported there. This time subsequently we repeated the experiment and mercifully we have satisfied ourselves that the introduction of the cell into the counter with the cell not operating does not change the counter. So that the paper is complete, we'll probably be sending it to some journal for publication. The next paper was another experiment, a continuation of our ICCF-5 work, where we had reported using electrically self-heated palladium, and we recently used palladium-rhodium foils strips. This was incidentally supplied by the Kimbra people in Japan, and we thank the people for readily supplying us these foils, about 100 micron thick, and these were heated by passing a current in a deuterium gas. We were able to get reproducible loading and unloading, but unfortunately we got no neutrons in several trials. Experiments are of course continuing, but so far we have no positive. If only that would, since the loading is almost 100% reproducible, if we had got neutrons, we would have been very happy. There is a device which you can switch on and show to the skeptics. But the other experiment is a continuation of the work where we first reported at Nagoya anomalous emissions from palladium hydride. One is not even sure whether it is related to the topic of cold fusion, but it is something which is 100% reproducible. I can show you a few very nice looking autoradiograph which we have taken in the last few months. I'll come back to that. And lastly, again, a technique, electronic imaging of tritium on the surface of solid samples. We mentioned about this again last year. I think I have a few slides on that. Let me just complete the area. These are the experiments, the second category, where we are doing in collaboration with other divisions in VAC. And the first one is electrolytic loading of tritium-labeled hydrogen into palladium again. Essentially, we are using for the electrolyte LiOH, but with a large quantity of tritium, highly radioactive, of about 10 millicurie per ml, which gives a tritium to hydrogen ratio of 10 to the 1 ppm, which is a large amount, and because it's highly active, it can be done only in a lab which is familiar, they have blow boxes and so on. And the idea is as follows. I think it would be a very interesting experiment to try and answer the question, during electrolytic loading or any other loading, does the hydrogen get loaded uniformly, or does it go and sit in special pockets? Everybody has been suspicious that there are special regions, so if only we can use the tritium-labeled hydrogen and do an autoradiograph, we'll be able to find out whether there are such hotspots. So far we haven't got any indication to that, but the experiments are going on. The other experiment which we are carrying out, this is being done with the fuel reprocessing division, which is a plutonium reprocessing plant, and they have all the facilities for handling highly radioactive solutions. The other experiment is done jointly with the analytical chemistry division and the radiation systems division, and this is tritium generation in commercial nickel-cadmium batteries. We, if you recall, reported at the Nagoya meeting 1992. We are probably the first group to report the production of tritium in ordinary light water cells, which was subsequently confirmed by Dr. Notoya and others in Hokkaido, and since then many other groups in light hydrogen loaded systems. And as a continuation, we ask the question, is it possible that tritium is being produced in ordinary commercial nickel cadmium cells? So I have something to report on that, I'll come back to that. Effect of magnetic field on resistivity of hydrogen loaded nickel wire. This is a continuation again of the work reported. Our attempts to try and reproduce a Piantelli experiment. But there is one interesting observation on the resistivity, which Dr. Starr just now mentioned. I think you will be interested in looking at this, and I would appreciate his comments. I'll come back to this also. Transportation of elements during germination of seeds being done with the biotechnology division and analytical